to use, dog. I got to send it to my wife. Believe this. All right. Let's talk about centralizers. One thing you got to remember when you're drilling with casing or reaming with casing or reaming with liner, do not run bow type, bow spring centralizers. What do you think is going to happen if they get hung up? A blade's going to break off, and it's going to fall to the bottom, and it's going to damage the bit, and you're not going to get pipe to the bottom. Y'all familiar with what bow springs are? Pretty much shaped like this. They've also got what's called now high-tech bowspring called a bow sub. It's actually screwed on to the casing, and the way it's designed, the bows stay non-rotating relative to the wellbore, and the internal pipe actually rotates. But the problem there, what happens if it doesn't do what it's designed to do, and it doesn't, and the bow starts rotating, well, it'll dig into the wall, but it's got a lot of side force in there, because you have to have the standoff. It could break off while you're rotating, fall to the bottom, damage the bit. So just remember, you want to use some type of solid blade. Centralizer sub, which is screwed into the casing, it's an integral blade. There's a company called Wear Socks. They have a spray metal technology where they actually spray, custom design the centralizer onto your pipe. They actually use a spray metal process to spray metal, if you will, onto the pipe to design it to your specs, how many blades, how high, how thick you want those blades to be. And Weatherford, we have what's called a drilling with casing centralizer, and it's, this is what it looks like right here. It's basically cast steel, one piece, no welds. Another thing, when you run solid blades, solid body centralizers, you don't want any welds in there. Similar to why you don't run welded blade stabilizers in conventional, because what can happen, it can come off or wear out or break off in the hole.
How do you locate those on the pipe? Do they just butt up against a...
What, this right here?
Yeah.
This is actually one piece. It's cast just like this.
Okay.
It's all one piece, solid blade. So this is all one piece of metal right here.
Sure, and where do you put it on the... I mean, does it just butt up?
On the pipe itself.
Yeah, on the pipe itself.
It depends. Great point. What we do, we get with the operator, BP, Shell, ExxonMobil, whatever. We run a centralizer program. What is your minimum required standoff? So if they require 70% standoff, as the program will output where the centralizers are placed once every 40 feet, once every 80 feet, every other joint, wherever to put on the pipe. And typically we'll run stop rings about 5 foot above, 5 foot below the centralizers. But what I tell operators, only put them where you absolutely need them. Because if you start running 40, 50, 60 centralizers, what's going to happen when you're having problems getting casing to the bottom in conventional operations? You're going to pack off and you'll never get that pipe to the bottom. So just put them where you actually absolutely need them, where the BLM or the Bureau of Land Management requires you to put them. No more, no less. Beauty of this centralizer right here, it's got an internal rubber lining. So this centralizer is what we call non-rotating. In other words, the blades don't rotate relative to the wellbore, but the pipe, if you can picture, rotates inside the casing, inside in the centralizer. What you have is a 90 durometer elastomer lining in here, which is fluted, and this actually reduces the coefficient of friction about 50, 60%, because you don't have steel on steel. Now you've got rubber on steel. So in essence, you've reduced your torsional requirement there. It's got the vent hole, it's got the fluted lining right here. If you get any debris trapped in here, it'll come right out. It also has, I don't know if you can see it, it's got vent holes right here, which purges trap pressure, and also it's another outlet for debris. Because if you get any debris buildup, it could go from a non-rotating centralizer to a rotating. It could lock up and rotate with the centralizer, which isn't a deal breaker. You just might see a little more torque, but it won't do what it's designed to do. So this is almost the most perfectly designed centralizer for drilling with casing applications. Any question on that? It's also expensive as hell. I won't kid you. Go ahead.
So they just free flow between the stop rings, right? On the...
Yes. I don't like to have this is like my own rule of thumb. I like to run them 5 foot above, 5 foot below, just to give you 10 foot of play. If you put them too close, or if the stop rings too close, it could, it's a place like a junk basket to trap debris, so it could go into a rotating centralizer. So give it a little play. Sometimes you can run them between collars. If you got collar pipe, you can run them up and down there. But I like to have them in one position, not move up and down by the pipe while you're drilling with casing. It's just a cleaner operation. Any more questions on that? Dickie, no questions? Okay.
All right now.
Cool. Drilling with liner. Okay, how many of y'all are familiar with liners, what a liner is when you run liners? Okay, basically a liner is casing that's not run to surface. It's hung off into the previous pipe. What our drilling with liner system typically looks like, you start off, you can run a casing bit or a conventional bit on bottom. We like to run multiple flow collars, as I said before, have redundant valves in there because you're circulating for a long period of time. So we either run multiple single valves or a double valve flow collar in there. You can run a single or dual wiper plug system, just depending on your cementing requirements. We have what's called a mechanical ball seat. Basically, when you drill the liner to TD, you'll drop the ball. It'll sit in this ball seat, which is located at the top of this liner here. The advantage of this ball seat versus conventional ball seat is that when you pressure up to a certain pressure, say 2,500 PSI, if that's what the shear pins are set for, the formation will never see that 24 PSI. It'll be dissipated by this energy absorption tool prior to being seen downhole. Sometimes the ball seats are located close to the flow collar, so when you blow those things out, when you get ready to set your hanger or release the running tool, the formation will be exposed to that pressure surge. You got a pack off in here. When you're doing cementing, the running string will be sealed against the liner itself. Your running tool, this is latched into a profile in your packer. This gives you the ability to rotate the liner. You have a packer actuator, rotating packer actuator. The way you set your liner top packer is at the end of your cement job. You pick this up, you set it down on top of your PBR, X number of pounds, and that'll set your liner top packer. It's a mechanical event. You got a floating jump on it right here. It prevents debris from falling in on downhole on you, which could potentially pack you off, precluding you from pulling the running tools out of the hole at the end of the cement job. Okay.
You say the packer sets to the right, or is it just a no-go in the PBR?
Yeah, this is a no-go on this actuator. So all this while you're drilling is seated inside the liner right here. The only thing sticking up is this jump bottom. So just imagine this inside the liner, right? When you're done drilling it in, you're going to release this running tool. You're going to set the liner hanger. You're going to do your cement job. When you get through your cement job, you're going to pick this packer actuator, which does have no-go dogs on it. You're going to pick that up above the PBR. Those no-go dogs come out. They're going to sit on top of that PBR. Depending on the size of the packer, anything from 40,000 to 80,000 pounds of slack off weight is going to expand that packer element and you set your packer.
Can you explain to them how the no-go dogs work there, Steve?
Yeah. Basically, it's a set of dogs, part of your running string, and they're collapsed inside this liner right here. So when they come out above the PBR, they go from a collapsed position, they expand pretty much. So now you'll never be able to enter that liner again. So they sit on top of your PBR, you slack X amount of weight down on top, and that extrudes that liner top packer element. I know I could give a whole, well, I'd get somebody in here to do a whole course on liners, but that's another subject. Might be pretty good. But anyway, what I want you to get out of here, you can drill with liners just like you can with casing. And the reason I'm preferable to drilling with liners because you can make connections every 100, depending on what size drilling rig, to 135 feet, because you're drilling with the drill pipe and not casing. How long do you think a joint of casing is? 35, 40, 45 feet, so do the math, you're making a lot more connections. What happens when you make connections in depleted sands? The more connections you make, the more you're prone to differential sticking, because what's differential sticking? Pretty much sticking on the slips while you're not rotating the pipe through a permeable sand, a depleted sand. So you want to keep that pipe moving, and drilling with liners allows you to keep it moving depending on the size of the rig, 100 feet, sometimes 135 feet, just depending on the amount of drill pipe that rig can stow away in the derrick. Now, any questions on that? But other than that, it's the same, you get the same benefits. You get the smearing effect, you get the plastering effect, you see less losses as you would in conventional operations. This is a example. We did about a 10-well program for Pemex in Mexico, and basically the deal was they had a formation probably 2,000 or 3,000 feet below this 9 5/8 inch shoe. There was a thief zone, a really fractured carbonate, which when they drilled conventionally, total losses, stuck pipe, multiple sidetracks, several $1 million to get back to where they were before they sidetracked. So what Pemex wanted us to do, after we set this 9 5/8, they would drill the 12 1/4 inch hole through a shale section, stop about 50 feet above that fractured El Abra or fractured limestone formation. Come out of the hole, pick up a 9 5/8 or sometimes a 7-inch liner drilling assembly, and then drill the liner X number of feet into that El Abra caprock, maintaining total returns, getting the 7-inch or 9 5/8 inch liner where it couldn't have been gotten with conventional methods. And I think out of the 10 jobs, we got 9 successful runs. There was one run where they actually, while they were reaming the hole, they didn't set the shear pins high enough on the liner running tool where the liner actually released and they had to pull the liner out of the hole. That's the only downside of hydraulic liners. You're limited with how much surface pressure you can pump while you're drilling the liner in, because if you exceed that pressure, you're not going to drop the liner in the hole. You just unlock the running tool. You can't rotate anymore. You got to cement where it is. Another reason you need to do your hydraulics up front. Any questions with us about this? Show you a couple more case histories. This was in Indonesia. The operator was CNOC, the Chinese drilling company. They had 2 sidetracks trying to drill through this limestone, this fractured zone right here. So what they did, just like in the previous well, they drilled conventionally to above this fractured zone with an 8 1/2 inch bit, came out of the hole, picked up a 7-inch liner with an 8 1/2 inch casing bit, drilled through here, sustaining total losses, lost returns. But what happened, like I explained this morning, they were able to manage the annulus backside with the pump tied into the trip tank. So the losses were a lot less with the liner drilling than they saw with conventional drilling, which even though they were getting 100% losses, they were able to drill into the shale and got a good leak-off test, which they couldn't have done with conventional methods. Any questions on that? So you basically liner drilling similar to casing drilling, except you're drilling with a liner, and you can make connections every 90 to 135 feet versus 40 feet with the casing. Now, when you're drilling on super single rigs, you're still limited to a single joint drill pipe there. But most of the liner drilling we typically do Gulf of Mexico type operation when you got the big dares. Any questions? This is one we did for your old buddies there on Nikika K3. Basically, there was a depleted sand called the K1 sand. It was depleted down to 6.5 pound per gallon, and we were fearful drilling this conventionally, we would get stuck. So we worked with BP I worked personally with them for about 2.5, close to 3 years in designing this job, since this was their first deep water well. Deep water, not well, but drilling with liner in a deep water well. So the plan was to drill conventionally to the top of this depleted sand and pick up a 9 7/8 by 14-inch liner, since the previous casing was 14 inches. Drill the remaining shale, drill the liner, try to get another 300 feet, get them into a shale where they can get a good shoe test to drill their subsequent 8.5-inch hole to set 7 5/8-inch liner, production liner. So the way it went down was this. Pipe got set okay, the 14-inch, they drilled out, and they were seeing losses right away, because we were only about 50 or 60 feet above that depleted sand. So what we think, that sand was communicated with the shale up above. So we managed to stabilize the well. We pulled the drill out BHA out of the hole. We picked up the liner, started reaming, started taking losses, but we lost total returns. We were able to keep the backside full. We had a riser booster pump tied into the riser, and the rule was the Bureau of Safety Environmental Enforcement, the regulatory authorities in the Gulf of Mexico, said they had to see some type of returns at the surface for us to continue drilling. So when we were drilling this thing down, the hole stayed static on connections, and we always saw fluid coming across the shakers at the surface. When we were drilling, it was still total losses, but we were still circulating with the booster pump, so there was still some type of, it never went down low enough where you couldn't see any returns coming to the surface. This is a little profile here. This is the shale we drilled up above the depleted sand, and you can see we were losing probably 280, 290 barrels an hour. Once we hit the sand, we started losing over 300 barrels per hour, and we went back in the shale, went back to about 280 barrels per hour. So something was helping us out in this depleted sand, because the geomechanics guys were predicting losses upwards of 1,000 barrels per hour based on the permeability readings. So we were getting some type of smearing effect there. Something was working in our favor where the losses were just a little over 300. So any questions on that? Okay. Planning, key to successful drilling with casing, drilling with liner operations. What are the current industry trends? Easy prospects have been drilled. Remaining wells are hydraulically challenged. So solutions like managed pressure drilling and drilling with casing have become more and more prevalent. Management of wellbore pressure profile requires greater precision. Well complexity requires integrated solutions. That's why it's important for well engineering collaboration at the onset of the project, where you can align the service provider with the operator's team. The big thing to remember here is the service provider knows his tools and knows how to manage those tools better than the operator. Let the operator manage the well, let the service provider manage his tools. Well, what do you think about that?
It'd be nice if it worked that way.
That's the way it should be. Yeah. I like this slide here. Well engineering collaboration to minimize risks. Moving beyond you call, we haul. What does that mean? Don't call me 24 hours before the problem. Have this thing planned up front. Project life cycle. Many times we get involved in the execution phase. Again, my point, let's get involved early on, like right up here in the conceptual planning phases right here, identifying challenges so we can indeed design the right solution for the problem way ahead of when the problem occurs rather than the night before. What are the advantages? Ensures availability. A lot of this is common sense. Availability of the right products and right services against attempting to source these in the execution phase. Service providers know their products and services and are better positioned to manage these, allowing operators more time to focus on the well, which is what the drilling engineers working for BP, Shell, ExxonMobil are paid to do. let us worry about our stuff. We're gonna align it with your program. It's all gonna work out one way or the other, but at least we plan this thing correctly. Service providers gain a greater understanding of the operator's well construction objectives, leading to the recommended products and services being properly aligned with the operator's objectives. So we're both working together. The service company isn't going this way, the operator's going that way. Everything's aligned. Typically what the drilling engineers do, and these operators I work with, they'll take my procedure, incorporate it in their drilling plan, so it all makes sense. Early partnering with service providers ultimately reduces risk, leading to a greater chance of success for the project. And that's all I'll harp on this. Any questions on that? It all makes sense? Okay, I didn't come up with this. Some guy from Yugoslavia did. I can't even pronounce his name. Guana Meduric. It was his thesis paper at University of Zagreb. But basically, this is a pretty good depiction of all the engineering that goes into planning a drilling with casing and a drilling with liner job. You can see hydraulics, mechanical loading, torque and drag, buckling, cyclic stress fatigue, hole geometry, vibration comes into play. You got to know your elastic load limits so nothing comes apart in the hole, wear, casing wear, and fatigue. It's all tied in with each other. The key thing is do your engineering up front, make sure nothing comes apart in the hole. Especially drilling with liners. People ask, how can you drill with liners? Well, think of the liner as a well-designed BHA. Because what's the BHA? It's the part below your drill pipe. Except you only have probably 2 or 3 different components in the BHA, where the liner has several components. So you've got to manage those components of the liner. You got to make sure your running tool, your hanger, your packer, all that stuff is up to the torsional and hydraulic loading you see when you're drilling with liners. Any questions on that? This will all be loaded up to the internet. What are some of the planning tools we use? Electric and lithology logs to determine compressor strength. We like to look at the mud logs for lithology determination. This is probably, for designing bits, this is probably the most valuable tool, because this tells you exactly what's going on downhole. A lot of the log, we've actually gotten in a situation where the sonic log is reading like 50 or 65 microseconds per foot, which equates to 20 to 25,000 PSI unconfined compressor strength. We looked at the bit runs through that interval, and the freaking bits came out green. So there's kind of a disconnect right there. So we said, yeah, if these bits came out drilled green, our bits could definitely drill it. Lo and behold, we drilled a 500-foot interval, no problem. So you got to look at everything before you make a decision. Like I said before, biggest thing in casing and liner drilling, connection design, cyclic stress fatigue modeling. Typically, we get with Weatherford doesn't have its own cyclic stress fatigue. We typically defer to the vendors like Tenaris Hydro, VAM, Hunting. They have in-house software that if you give them your operating parameters, they can actually figure out, calculate based on your hole conditions, how many revolutions that pipe is good for before it comes apart in the hole. Any questions so far? BHA tendency modeling. Remember I said non-retrievable systems, you don't have steering capability. However, give you an example. If you want to maintain a 60-degree angle over 500 or 600 feet, we've got software that can actually predict build, dropping tendency, and maintaining neutral tendency. Typically, when you're drilling with casing, you're going from a bigger hole, like 12 1/4, into a smaller hole, like 8 1/2. So you're going to see a slight drop. So you want to compensate for that drop, especially if you want to hold that tangential angle over hundreds of feet. So what you do, you impart a slight build based on stabilizer size and placement to your BHA, which will let you get your goal, hit your target at the end of the casing drilling run. Now, thankfully, all the targets we've got are pretty big, so it's really gonna be hard to miss it. I'll turn down the job if they give us a 10-foot target, because I can't tell you, I can pretty much say you're safe, but I can't guarantee it. So we're operating with a pretty big window. When you start going offshore, platform wells, y'all familiar with spider plots? You see all these intersecting trajectories? I wouldn't recommend anything but a steerable VHA for that. And you don't know, last thing you want to do is collide with another wellbore. So, but yes, for retrievable, non-retrievable systems, we have the capability of predicting which way, what kind of drop we're going to get with the VHA or what type of build. We'll run torque and drag models to predict, what type of torque we're looking at. If we're going to go into a helical or sinusoidal buckling mode. Also, this will predict side forces, which you see in a lot of high dog leg situations. What you want to eliminate is side forces at the top of the hole, because if you want side forces at all, you want them at the bottom. If you have them at the top, you're going to, because that's where all your weight is seen, your actual loading. That's where you're going to get your highest amount of wear on the casing. So keep those dog legs in the lower part, minimize them at the top of the hole, basic direction of drilling. Risk analysis, at the end of the day, we like to work with the operators and come up with what can go wrong in a drilling with casing and drilling with liner. And if it does go wrong, how do we manage it to make sure it's not a total catastrophe? Because not everything works 100%. Bless you.
Thank you.
Drillability. Any questions? Any questions so far? Yeah.
What are the risks? Did you answer?
Oh, okay. Yeah. Now that you're on, how much time you got, Lee?
Well, I mean, that's, some people might have to go at certain times. There's no other class, but whenever people have to go, I understand.
That's a good point. This is great. I got a risk assessment table right here. Told you I could make this a 6-hour presentation if you want.
Let's keep it under 6.
Okay, this is a good example here. This is for an operator in the Gulf of Mexico. Okay, one of the hazards, this is before we even get out to the location, damage to the 8.5-inch bit. Basically, in these risk assessment programs, we want to figure out everything within reason that can possibly go wrong, from transport of the VHA to the actual drilling to the drill out of the VHA. So here, for example, damage to the bit, equipment damage, small delay, likelihood of occurrence is low. What we would do, we would put some boards around the bit to prevent damage to the bit in transport. Let's go something a little more serious. Bit plugging right here. Could cause a delay in schedule, moderate delay. Carefully select jet size, ensure pumping when tagging TD. One of the procedures we implement in drilling with casing is maybe 1 or 2 joints above the existing TD. You want to kick on the pumps, because the last thing you want to do is tag bottom without the pumps on. You have a chance to plug in the nozzles. So basically, that's how you would mitigate that problem. Let's see, lost circulation. What would that be? You'd have a delay in schedule, be only a moderate delay, high likelihood of occurrence in this situation because we were drilling through 4 depleted sands. Ensure sufficient mud supply on the rig. We have actually, believe it or not, drilled a liner and the operator ran out of mud, so we had to call it short. We warned them to make sure you had enough mud out there. Decrease pump rate, pump lost circulation material, in sweeps, control drill. Let's talk about lost circulation material with drilling with casing, drilling with liner. You have to be careful to minimize the amount of fiber you pump. Fiber is what can plug your bit and plug your flow collars. So consult with the drilling with casing engineer if you need to pump lost circulation. If you're pumping more than 20 or 30 pounds per barrel, we recommend doing what's called a laboratory test or a control test where we actually pump that amount of LCM, that same formulation, through a model of the BHA we'd actually be drilling with to ensure nothing that gets plugged up while we're drilling the casing. The last thing I'd want to do is everything going good and the operator wants to pump a bunch of snake oil LCM, as I like to call it, down the pipe, and you're plugged off, you're done. And you haven't even solved the problem. You got to re-drill it again. So be really careful with the amount of LCM. I know when I was a drilling engineer with Conoco, I got taken out to lunch by a lot of these snake oil LCM salesmen, you know, but that didn't impact my thinking at all. But just be careful with what you pump down hole to make sure it's compatible with all the tools you're putting in the string. Here you go. Here's a big one. Drop foreign object in the hole. How many of you guys work on rigs have one of your roughnecks drop something in the hole, a hammer, slips, or whatever? Okay. We've actually had an instance in our first drilling with casing job in Colorado, this peons thing. Nobody fessed up with it, but we think one of the roughnecks dropped the business end of a ball peen hammer in the hole. We started drilling. I remember I was in the hotel room in Rifle, and my hand was drilling casing. He calls me up and says, Steve, I can't increase the penetration rate. I asked him a bunch of questions. He says, well, Randy, what do? We got to pull out a hole and see what's going on. Pulled out of the hole. Sunday morning I was out there. Lo and behold, embedded in the blades of the bit was the business end of a ball peen hammer. If we didn't see that, it was a blessing in disguise, and it happened on Sunday morning. But anyway, if we didn't see that hammer, it would have shut down that whole drilling program, because the operator would have said, Steve, your bit ain't worth the shit, you know, it's not making hole. So thank God that hammer came out with the bit, so we knew what the problem was. Everything else was all downhill. But that was pretty cool. We called it the drill shoot, the Defier fishing tool. So, you always want that hole plug, that rotary plug, whenever you pull it out of the hole. Just common sense. You got to talk about that in the pre-tower meeting. Make sure that hole is plugged. Another thing, and this happened on the Nakik well. I couldn't believe it. They were filling the pipe with the mud hose, and I was standing on the floor with my night guy, my night relief, and we were saying, James, this guy's getting way too close. He had a piece of cloth hanging off his belt, I think, and he was, actually that cloth went down inside the pipe. I knew that was going to happen. And anyway, bottom line is, they spent about 2 or 3 hours running these makeshift fishing tools inside the liner to pull the thing out. You know, he had some type of cloth on there. I just saw it happen, you know, and it happened. So just make sure in your pre-tower meetings that hole is covered up when your pipe is out of the hole. Let's see. This one I want to talk to you about, new technology. I know y'all are getting tired. I'll make this the last one. Lets me go farther. Remotely operating cementing methods, Valhalla North Sea. Okay, remember we talked about stage tools very briefly, hydraulic and mechanical stage cementing tools. The problem with these tools, even though it's a mechanical tool, it's going to see pressure when it opens up. The hydraulic tool, you know it's going to see pressure by the name hydraulic. So what the operator was looking for here, he was looking for a cementing method other than doing a cementing method through the casing bit after we drill a liner in, where you would not see a sudden pressure surge to the formation. So you had to think out of the box a little bit. And Weatherford had acquired a company called Petrowell, which makes RFID, radio frequency identification tools. And they use it mainly for explosions. But they had a design for a 2 7/8 to 4.5 inch stage tool that they use for small pipe. So we got with these guys, and they said in so many weeks they could design a 9 5/8 inch one. So the light bulb went up. That was the solution that the operator was looking for. Let me just go through this real quick. The field history, it's located about 180 feet. In fact, I'm going to be presenting a paper on this. This is the short version of it at the convention drilling conference in Fort Worth. 180 miles south of Stavanger. Drilling commenced in 1969. They still have another 600 to 700 barrels of recoverable oil in place right here to get out. What were the problems in the Valhalla field? compaction, subsidence, and depletion. Because of the compaction, the whole seabed would sink, 8 to 15 feet. It would collapse and shear the existing casings. The biggest problem was because of all that, you had sustained annulus casing pressure causing the operator to have to do a lot of remedial cementing, which was offshore, millions of dollars right there. So poor cement jobs was the problem. So briefly, there's a formation here called the Lista Shale, and this is a 14.5 pound environment. And right below it, you have the productive core, which is a really weak chalk limestone. So when you started producing out of the core, and it's been producing for over 30 years, you have that phenomenon called compaction. All this stuff settles out. It's like stepping on a sponge, and it's a really good method of oil production because it's squeezing the oil out of that rock, but it plays havoc on the existing casing strings. So what they were doing was drilling liners from the Lista Shale into a high-pressured overburden into a depleted rock, which is a perfect application, because if you do it conventionally, you're going to stick the pipe. Well, we do it with liners, and we really want to stick the pipe, because what that does, you don't have to drill with 15-pound mud weight once you get in here. You drill the liner with 15-pound, you stick the pipe, and now they have what you call a straw in here, which is the liner. Now you're able to cut back the seawater and drill this remaining depleted formation. Okay, let me get back to the story. So yeah, no problems drilling the liner here. We all know it's going to get stuck. You're only drilling about 30 meters, 100 feet. They couldn't get a good cement job because they were cementing through the bit. Okay, so what we came up with was spacing out an RFID port collar, a remotely operated port collar, spaced X feet above the bit here. Let's do this. Here's exactly what we started for the liner drilling. You would drill with a conventional BHA to X feet above this depletion, and you pick up your liner and drill it into the depleted tor formation. Okay, here's a good slide. Cementing solution, use proven non-retrievable DWL technology. Bypass cementing through the bit. No pressure surge to the formation upon opening. So we came up with radio frequency identification system versus mechanical hydraulic stage tools. So we would put that RFID operated port collar X feet above the bit. Below that port collar, we would put a metal expandable casing packer. This would act as a base, because when we cement out through this port collar, RFID port collar, your cement would go up, and the base of where that packer would prevent that cement from seeping into the depleted tor. Above the port collar, this is still being designed, is a casing swivel. From cementing 101, you get your best cement jobs when you're able to rotate the pipe. But if the pipe's stuck, there ain't no way to rotate, right? So what this company called Tercel came up with was incorporating a casing swivel as part of the liner. This casing swivel would be hydraulically and mechanically locked, so it wouldn't decouple while you're drilling it down. However, when you reach TD on a pressure event, it would decouple that swivel, allowing you to rotate above your stuck point. So now you have a base for the cement, you've got a port collar that doesn't exact any pressure surge on the formation, and you've got a way to rotate your pipe over the stuck point. So it's almost an ideal scenario for cementing, which hopefully will mitigate their cementing problems. That's pretty much it in a nutshell. And this is the picture of the BHA right here. You got your casing bit on bottom, the stabilizer, you got your flow collar, centralizer, your metal expandable casing packer, RFID port collar, casing swivel. Same liner system as before, except you got this existing jewelry. The way it works, you drill your liner down, you know you're going to get stuck. As soon as you start seeing losses internally to the pipe, you're going to drop your shut-off plug. That's going to latch your shut-off plug, excuse me, you're going to drop your ball that latches into your shut-off plug. It drives that shut-off plug down here to the flow collar. That seals your losses internally. Now what you can do, you're gonna pressure up in stages. Your first, when you see 2,500 PSI, that's gonna set the hanger. When you see 3,500 PSI, that's gonna decouple the swivel, give you the ability to rotate the pipe. 4,500 to 5,000 PSI is gonna expand this casing packer, and that's gonna stop losses on the angular side. So now, in theory, you stop losses both internally and externally. Now, what you're gonna do is pump a pressure pulse down to this RFID port collar, and through a series of designed pulses, it's gonna open up the port collar. But the port collar has a timer in it, so it's not gonna open up right away. So it's gonna read those pressure pulses, you're gonna bleed the pressure off, and after X amount of time, however many minutes you got that port collar set for, port collar's gonna open up, that sleeve's gonna open up, and lo and behold, you're able to cement. No pressure exacted to the formation. Questions?
That packer on the bottom to seal
Yeah.
off the cement from
Yep.
going any deeper, how does it expand it? Is it just with a metal cone
It's got elastomer elements in between metal. It's the same print. It's not a metal cone. It's hydraulically expanded, but it's expanded similar. It's basically it's an expandable piece of pipe that's mounted on the 9 5/8 inch line. It's got some tubes manifolded in there, so the pressure is diverted to the expandable element. So at 4,500 pounds, it starts the expansion process.
or kind of similar to an IVP, sort of? Except
What's an IVP?
inflatable bridge plug?
Similar, but this is
But it's
metal.
in a
This is
case.
metal right here. Now, most of your angular casing packers have elastomer elements which will not hold up in drilling with liner scenario. So hence, this company, Weltex, actually designed an expandable packer. Came up with a design, it's a metal, so you actually have metal sealing to the formation. So metal's gonna hold up better than elastomer in a liner drilling situation. So hopefully, when all this stuff comes together, it'll mitigate, it'll stop the losses on the backside, give you a chute on which the cement can sit on, and then get circulated up to as high as you need it to be. Another thing, the beauty of these RFID port collars, you can put them wherever you want in the string. They're each open with a unique pressure pulse or a unique set of radio frequency ID tags. These tags, I got answers to your questions too. These tags are about 1 inch long and about 5 millimeters wide. Very small tags, and they're good from 17,000 PSI up to 30,000 PSI. So really depth, there's no limitation on those things. So that's a huge advantage right now. It takes the geometric problem out of it. Because if you've heard of 2 and 3 stage cement jobs, you've got to drop different size plugs in there. It takes the plug management, because you can operate all this from surface. Each RFID port collar has its own unique sequence, so I can open up port A and don't have to worry about port collar A, B, and C opening up. And you can either shut it with a mechanical wiper plug or shut it with RFID tags and a timer. So it's got a lot of flexibility. I see its biggest usage in narrow pore pressure frac gradient windows. We've got cementing issues. And you couple this with the swivel and the packer, man, you got a perfect cement design right there. Okay, I got some more slides. If y'all want to hear some more? No. Yeah.
I think this was already a ton of stuff, Steve.
Yeah,
There's a lot of stuff for them.
I pretty much covered what I needed to. Here's one right here. Here's the connections that we've used: buttress, modified buttress. Basically, on the connections, if you drill location, make sure it's actually been used in a drill location environment, and make sure it's got the cyclic stress fatigue resistance per your application. Oh, y'all been a wonderful class, and I really enjoyed it. And I've got some cards up here if you have any questions. you want me to help you with your senior projects, I'm just kidding. Other classes have asked me. But don't hesitate to email me, send me some jokes if you want, I don't care. But if you got any questions, don't hesitate to call me.
Well, thanks, Steve.